Okay, so this one is called Lessons 4 and 5. We may not finish the entire lesson this week. We may finish the rest of it in the next week just because this one can go a little bit long. But basically what we're going to be doing is we're going to be going into talking about horizontal transformations. So far, we really only talked about vertical transformations, stretching them vertically, shifting them up and down vertically, but haven't really, and reflecting them vertically. We haven't really talked about horizontal transformations. Now, last lesson we did talk about horizontal reflections a little bit, but we're going to talk about other horizontal transformations. So let's kind of review them a little bit. So suppose I have a function f of x. I'll put that here at the top. What happens to my function if I add a number to x? What that does is it shifts it. Well, I don't like how I'm writing. That's kind of lame. Let me. I'm writing that. What it does is it's a shift or a translation is the fancy word for it. To the left. Whereas if you had x minus h, it would be a translation or a shift to the right. So if you add or subtract a number on the inside, it's going to be shifting your graph left or right. Now, we also talked about what happens when you multiply. My choice of letter there, let me back up. We also talked about what happens when you take your x, your input value, and you multiply it by something. Okay, now that can do two different things. If the absolute value of b, in other words, we don't really pay attention to the sign, if the absolute value of b is greater than 1, then what it is, it's a horizontal compression. It squishes your graph horizontally. Whereas if the absolute value of b is less than 1, then it's a horizontal stretch. It will stretch your graph horizontally away from the x-axis. Okay, so those are horizontal transformations that we talked about prior. Let's see how these affect trigonometric functions. So as you guys know, with sine, at 0 it's 0, at 90 it's 1, at 180 it's 0, at 270 it's negative 1, and at 360 it's 0. Let's see what happens though if I take the same function sine. Instead of just letting it be theta, I let it be 2 theta. Okay, well I've kind of set this up in a certain way. I still want to get the same outputs. I still want to get 0, 1, 0, negative 1, and 0 like I did over here. I don't want to change that. But it is going to affect the angles. So for instance, what would I plug in for theta so that I still get 0 overall? If you plug in 0 for theta, you just get 2 times 0 would still be 0. So if you plug in 0, you still get the same output because sine of 2 times 0 is the same thing as sine of 0. So they both give you the same output, which is 0. Okay, but what about this one? Sine of 90 gives us 1, doesn't it? So what can I plug in here for theta so that I end up with sine of 90? Because I know that sine of 90 equals 1. So what can I plug in for theta to get 90? Well, 2 times what number makes 90? Hopefully you know it's 45, right? 2 times 45 is 90. So if I plug 45 into this function, I'm going to get sine of 90, which is 1. So in case you guys haven't caught on to the pattern here, let's do one more. and then hopefully you'll get the pattern of that. How about, now I want to get 0 again. This 0 came from 180. So I want this to equal 180. What would you plug in for theta to get 180? You would plug in 90. In other words, exactly half of it, right? So what we're doing every time is we're taking the original angles that we would usually plug in and we're dividing them by 2. So if I divide this by 2, I get 135. And if I divide this by 2, I get 180. Now, so basically by putting this number in front or multiplying the theta by 2, it takes the angles that I would usually use to get these outputs and cuts them all in half. Let's see what effect that has on our graph over here. So we already plotted 0, 0. Let's do 45, 1. Now 45 is going to be in between 0 and 90. So it's going to be like right about here. And then 90 gives me 0. 135 gives me negative 1. Now 135 is between 90 and 180. So it would be like right about here. And then finally 180 is 0. So compare the graphs. By putting a 2 in the front, it squished it horizontally. And that kind of fits with what we learned about transformations in the past, right? We learned that whenever b, the absolute value of b, is greater than 1, it compresses your graph horizontally. It shortens the function's period. So in this case, the period is usually from 0 to 360, and then it repeats. But now, because of that 2, after 180, it's going to repeat. Okay, so on and so forth. So we have one conclusion so far. When there's a number in front, it's either going to stretch or compress our sine wave by that much. So here's some vocabulary for you here. What is a period? And what is a periodic function? In mathematics, let me lower my screen here a little bit so you guys can see. In mathematics, a periodic function is a function whose y values repeat over or along the x-axis. And the length of that interval is known as a period. So we have y value of 0, 3, and whatever that is. That pattern of y values, they just keep repeating over and over again, etc. So you get this green shape here. It just gets copied over and over again throughout the horizontal lifespan of the graph, called a periodic function. And each of those mirrored pieces, one full cycle, is what we would call a period. The length from here to here is what we call one period. So in this case, if we think of these all as ones, this would be -3 and this would be +2. How far away is -3 from +2? They are a distance of 5 spaces apart, right? And so we would say that this function has a period of 5. Every 5 spaces, it repeats. That's what a period is. It's how long it takes a function to repeat. Now, when we're talking about sine and cosine, their periods are usually 360 or pi, right? So like, here's sine. It starts here and goes up like that, and it usually ends at 360. So it usually has a period of 360, which you could also call 2 pi. Okay, that's usually the period. But as you can see, as you saw from the last exercise that we did, when you multiply your angle by a number bigger than 1 or less than 1, it's going to change the period. It'll either make it smaller or bigger. Let's look at another type of change, though. What happens when we subtract our angle by a number? Not multiply it, but just add or subtract. In this case, we're going to do subtraction. Okay, so once again, we have the same original sine value here. I'm going to graph it really quick. Looks like this, right? Now, we know that sine of 0 makes 0, right? So what would I plug in for theta so that I end up with 0 in here, so that I can still get 0 as an answer. What would I plug in for theta? So it's going to be 0. Hopefully you know it's 90. Plug in 90 here. 90 minus 90 would be 0. So you'd have sine of 0 equals 0, right? Now let's do the next one. We know that sine of 90 equals 1, right? So what would I plug in here so that after I subtract these, I get 90? Therefore, my answer still comes out to be 1. That would be 180, right? Plug in 180 there. 180 take away 90 is 90, and sine of 90 is 1. So to get 1, you would have to plug in 180. Now, what's the pattern here? What you're noticing is that usually you plug in 0, but now you have to plug in 90. Usually you plug in 90, but now you have to plug in 180 to get the same outcome. So what's happening is everything over here is exactly 90 degrees more than everything over here. So what would you have to plug in over here so that you still get a 180? It'd be 270. How about over here? 360. And then finally for this one, 90 more than that is going to be 450 degrees. Okay, so let's graph this really quick and see what this looks like. So we have 90 is 0, 180 is 1, 270 is 0, 360 is -1, 450, which would probably be like right about there, is back to 0 again. Now take a look at these graphs. It didn't change the period this time. It didn't compress it or stretch it. But what it did do is it just shifted it over. And as we said before, whenever you subtract a number from your input, however much you subtract, that's how much things shift to the right. So these graphs are identical. It's just that this one's been shifted to the right by 90 degrees. Okay, we call that a phase shift. A horizontal translation of a periodic function, where you take a trigonometric function and you shift it over, we call that a phase shift. Okay. Now in this case, this is a little bit more complicated. We're doing both. So we have a phase shift, but we're also compressing it. And those two things kind of work together to create two different outcomes. So what would you plug in for theta so that you get sine of 0? We know that sine of 0 equals 0, right? So what would you plug in for theta here so that this whole thing comes out to be 0 and the answer comes out? Some of you guys might realize it's 45. Now, if you don't know how to get that, let me give you one more opportunity to get that mentally, and then I'm going to show you guys a different way to get it. And this different way is how we're usually going to do it. Okay, so let's give it one more try here. 90 gives us 1, right? So sine of 90 makes 1. So what would you plug in here so that this whole piece comes out to be 90, so that our answer comes out to be 1? What could I plug in for theta so the whole thing comes out to be 90? Well, hopefully you know it's 90. Now, if you don't, that's okay. I'm going to show you guys how to get it. And now this way is going to be the way that I'm usually going to do it, because it's not always going to be just so easy that you can do it in your head like that. So for those of you guys that could do it in your head, don't get too comfortable with that. I want you to know how to do this. Here's what you're going to do. You're going to take the angle that you want. We want 90. And we're going to set it equal to this. And we're going to solve it just using algebra. Add 90 on both sides. Divide by 2, and you get 90, right? So let's try that again with the next one. So for the next one, right? I know that sine of 180 equals 0, right? So I want this to equal 180. 2 theta minus 90 equals 180. So I'm going to add 90 over there. That's going to give me 270. And then I'm going to divide by 2. And that's going to give me 135. So now if I plug in 135 to this function, I get 0. So I'd encourage you to maybe consider pausing the video and trying to get the other two. And I'll put their answers up in just a second. Go ahead and pause the video, see if you can get these other two blanks and graph it. And then we'll compare answers. All right, so in case you didn't notice, by the way, they always go up by the same amount. So if the distance from here to here is 45 degrees, the next distance will also be 45 degrees, 45 degrees, 45 degrees. Or you can just set this equal to each one of these original angles and solve. But as you can see, it's a phase shift, so it did get shifted to the right, and it also got compressed. Now, some of you guys might wonder, hey, wait a minute, that says minus 90. Why didn't it get shifted over 90 degrees? It's because of this 2. Not only did it get shifted over 90 degrees, but this 2 compressed everything. So it got shifted over 90, yes, but then it got squished back halfway closer to the x-axis because of the compression. That compression affects the phase shift. You don't need to know this really, but just for fun, you can factor the 2 out like this, and that way you can see the phase shift. The phase shift is 45 degrees, and the compression factor is 2. Okay. But anyway, I digress. So that's a lot of talk that I'm giving you, not a lot of practice, but here it is. So horizontal transformations and trig functions. We've already talked about the A, that's the vertical shift. We've already talked about the K, that's the, I'm sorry, the A is the vertical stretch and the K is the vertical shift. Today we're talking about these. The B value results in a horizontal stretch or compression and changes the period. The H value here results in a horizontal translation, also known as a phase shift. So let's go ahead and graph these. The directions on how to graph these are going to be a little bit different. Now, as you guys know, what it's really going to change is it's going to change the angles we use, right? The angles that we usually use for cosine are 0, 90, 180, 270, and 360. Those are the angles that we usually use, but we're going to transform them. I'm going to take the argument here, 4 theta plus 180, and I'm going to set it equal to my first angle. I'm going to minus the 180, and then I'm going to divide by 4. And I end up with negative 45. So now usually with cosine I would start at 0, but because of this phase shift and compression, we're going to be starting at negative 45 now instead. Let's do it to the second angle. Usually for cosine, the second angle we plot a dot at is 90. But now it's going to be transformed by these horizontal transformations here. Same way, we're going to minus the 180 on both sides. And we're going to divide by 4. Now 90 divided by 4 is going to be a decimal, it's negative 22.5. So usually my second angle is 90, but now my second angle is going to be negative 22.5 because of these phase shifts and horizontal compressions. And we're just going to keep doing that. But actually, I'm going to show you something that makes life nice here in just a second so that you don't have to do this a whole bunch of times. But for now, just bear with me. I'm going to do it one more time. Minus the 180. Divide by 4. So as you guys can see, all I'm doing is I'm taking the angles that I would usually use for cosine, I'm setting them equal to this expression here and solving, and that's going to tell me my new angles. Now you could keep doing that to find the last two, okay, but I want to show you guys a shortcut. All you really need to do is you only need to do it the first 2 times. Because once you've done it the first 2 times, you can figure out what the other ones are by just doing some math, basic math. How far away is 45 from 22.5? Well, it turns out that if you were to subtract this number from this number, you're going to end up with 22.5. It's going up by 22.5 to get from here to here. Well, it always goes up by the same amount. So the distance from here to here, if you go up 22.5 again, now we're at 0. Now instead of calculating it, what would it be if I added another 22.5? What would the 270 then become? Starting from 0, if I add 22.5 to that, I'm going to end up with 22.5. And then the last time you do it is one more time, add 22.5, you're going to get 45. They always go up by the same amount. So really you only need to do the first 2 the long way. The long way is where you set this thing equal to the angle involved. But after you've done the first 2, just find out how far apart they are and just keep adding that much every time you keep getting the rest. So anyway, let me restate some things before we move on any further. So usually with cosine, what do? We start by putting the angles on the graph. And the angles are usually 0, 90, 180, 270, 360. But because of these horizontal transformations, we now know that it's negative 45, negative 22.5, and 0, 22.5, and 45. So that's the new part, okay? Negative 45 is my first angle. Negative 22.5 is my next angle. Then 0. Then positive 22.5, and then positive 45. So now I'm going to be starting here at this point. Now with cosine, where does cosine usually start? Well, actually, you have to plot your midline first, right? Now there is no midline, so that's 0. So my midline is right here across the x-axis. Okay. My amplitude isn't there either. That means my amplitude is 1. So I'm going up 1 and down 1. So my amplitude will be, my maximum height would be here. My minimum height will be here. Now, where does cosine usually start? Does it start at the max, the midline, or the minimum? Hopefully you guys remember it starts at the max. So since this is the first angle I'm going to start at, I'm going to be starting at the maximum point. And then we go down, down, up, up. So it's going to look something like this. Okay? And there it is. So usually, with cosine, we would start at our midline, right? Or we plot our midline, we do our amplitude, and we would use the angles from 90 to 360. But in this case, we still have the same midline and amplitude, but our angles are completely different, and that's because of these horizontal transformations. So we'll do another one here. There's a lot going on there. Student practice. I'm not too sure you guys are ready for a student practice. Let's kind of treat it like a guided practice. So first of all, if you wanted to graph sine, you need to start by finding your angles. Okay. Now, what are the usual angles that we use for sine? Pause the video here if you need to. Think about it. Look through your notes. What are the usual angles that we use for sine? They are usually the same ones we do for cosine, which are 0 and 90, 180, 270, and 360. Those are usually the angles that we use for sine. Now, we're going to transform them though. How do we transform them? We would take this piece here, 2 theta minus 1, and those are our horizontal transformations. Those are the things that are going to change our angles. And we're going to set them equal angles there and solve. So I'm going to add 80 and divide by 2. So I want you to do that for the first 2 problems here and see what you get. Pause the video here and work it out. Go ahead and find the 2 transformed angles. All right, this is what you should have gotten. You could have gotten 40 for the first one and 65 for the next one. Now we could repeat that for the third one, but we have an easier way. What's the easier way? Think about it, see if you can figure out what the easier way is, and then unpause the video and see if you get the rest of the angles right using the easier way. The easier way is to figure out how far apart are these and in what direction are we going. Well, we added 25 degrees to get from 40 to 65. And that's exactly what you do to get to the next one. We would add 25. So if you add 25 to 65, you would end up with 90. If you add 25 to that, you can get the next one. That would be 115. And if you add 25 to that, you get the last one, which would be 140. So usually we would, for sine, we would be using 0, 90, 180, 270, and 360. But now we're going to be using the angles 40, 65, 90, 115, and 140. Okay, so we're ready to graph the sine function here. So go ahead and pause the video here and see if you guys can graph this thing. Make sure you use our new angles to graph. So there you guys go. There's our angles we found, 45, 65, 90, 115, and 140. Notice that since this is the sine graph, we start at the midline, which is 0. We go up to 1 because that's the amplitude, and continue the pattern from there. Notice the gap I left here. Why did I make that so big? Well, notice that the distance from here to here is 25 degrees, right? But this is supposed to be 45 degrees. So this distance should be roughly twice as big as this distance if you want to get your measurements and scaling correct. It would look approximately like that. Okay. So let's do another one. Let's graph tangents. So tangent. What angles in degrees, we're only going to be doing degrees today. We'll get into the radians a little bit later. So what angles in degrees do we usually use for tangent? Well, from our last lesson, we learned that the angles we usually use are negative 90, negative 45, 0, 45, and 90. Those are the angles that we usually use when we're graphing a tangent function. But we're going to transform them now with our horizontal transformation. So I'm going to set those angles equal to 1/2 theta minus 90 to solve. So I'm going to add 90 to both sides. I'm going to multiply both sides by 2 to get rid of it. And so usually we would start at negative 90 for tangent, but in this case we're going to be starting at 0. Let's do the next one. We're going to set negative 45 equal to 1/2 minus 90. 0 wrong, theta. There we go. All right, so we're going to add 90. Then we're going to multiply both sides by 2. And now we end up with 90. So usually we start at negative 90, but now we're going to start at 0. The next angle after that is usually negative 45, but now the next angle is 90. But for the rest of them, we're going to use the shortcut. So how far away is 0 from 90? Well, that's going up 90 degrees, right? So to get to the third angle now, we're going to go up 90 again. So if we're at 90 and we go up 90 more, then that puts us at 180. And if I go up 90 more, that puts me at 270. And if I go up 90 more one last time to get to the fifth and final angle, that puts me at 360. So now we're going to use 0, 90, 180, 270, and 360 for tangent instead of the usual set that we would use. And we're ready to graph. So with tangent, the way we graph it is we start by putting the angles, but now we have different angles that we're going to be using. than usual. 0, 90, 180, 270, and 360. We're going to, when you're doing tangent, the next thing you do is you plot the vertical asymptote at the first and last angles. Then you plot the K value, but it's not there, so it's at 0. And tangent, as you guys know, is right and up, left and down. So since my stretch factor is 1, I'm going to go over to 270 and up 1, and then left to 90 and down 1. I didn't get my bending right on that. Like this. There we go. And that's how you'd graph that. So once again, all this does is it just changes the angles. After that, we just graph like we normally would graph. Okay. Why don't you guys try the next one here on your own? Cotangent. Go ahead and pause the video here and try to get as much as you can. I'll put the answers up in just a second. All right, so the angles in green up here are what you would usually use to graph a cotangent graph. However, after you set those values equal to the inside amount here, wrong way, and solve, the angles circled in blue down here at the bottom are what you would get. And notice I only did my math for the first two, and then after that I noticed that we're going up by 22.5. So I just kept adding 22.5 to find the other angles after that. So now we're ready to graph it. And there's our graph. Okay. Okay, we're going to do another example. This one's going to involve cosecant, and we have the outside numbers now as well. So let's see if you guys remember how to graph cosecant really good. So first of all, when it comes to graphing cosecant, you guys remember that the first thing that we do is we graph the reciprocal of cosecant first, which is so we're going to graph the sine function first. And as we've already talked about today, when you're graphing sine, you use the angles 0 and 90 and 180, 270, and 360. But those are all going to be getting transformed into something else because of our horizontal transformations. So 3 theta plus 90 equals 0. We're going to start by minusing the 90. And dividing by 3. So the starting angle now will be negative 30. Let's find out what our second angle is. Second angle is 0. So as you guys can see, we're going up by 30 there. So let's repeat that pattern there. So we're going up by 30 every time. So the next one's going to be 30, 60, and then 90. So the angles I'm going to use to graph my sine function first is going to be negative 30 up to 90 going by jumps of 30. And then after that, we'll graph what we actually want, which is the cosecant. Okay, so here we go. Negative 30, positive 30, 60, 90. Now when you're graphing sine, this is going to be our midline, so negative 4. My amplitude is 2, so I'm going to go up 2, down 2. And with sine, we start at the first angle at the midline, right? And we go up. to the max, and back down to the midline, down to the minimum, back up to the minimum. So there's our sine wave, right? But now we're going to actually graph what we want, which is the cosecant function. Cosecant function, as you guys remember, anywhere where the sine graph touches the midline, at those places we're going to have vertical asymptotes. And then the cosecant graph kind of looks like these little parabolas in between the asymptotes, and it touches the peaks and troughs of the sine wave. So there's that. Okay. So I'll let you guys try to do a cosecant graph. Go ahead and pause the video here and see if you guys can work out the solution. So I went ahead and graphed only one period here. So let's talk about a couple things. First of all, these are the angles you guys should have ended up with. Since this is a cosecant function, you start by graphing the sine wave, which means that you're going to start by using the angles that you would usually use for sine. But if you take these angles and you transform them with the horizontal transformations that we have in mind here, they will change into these values. Okay. The next thing I did was I plotted my midline, which is at 2. You can see I also used my amplitude to go up a half and down a half to find the max and the minimum. And since we're graphing a sine wave first, we start at the midline at the first angle at -90. We start at the midline and then we go up to the max, down to the midline, down to the minimum, and so on. So we get that nice little sine wave there. And then we're ready to actually graph the cosecant, which is we start by putting in the vertical asymptotes at the places where the sine wave touches the midline. And then we put our little parabolic in the graph. And you could graph more of them if you wanted to, but I didn't want to get bigger than it already is. All right. I think we can afford to do one more example, and then we're going to call it quits, okay? So let's do a tangent example real quick. All right, so as you guys know, with tangent, the angles that we usually use are -90 followed by -45. After that, we use 0, 45, and 90. For the first two, we're going to set them equal to the horizontal transformations. Multiplying both sides by 4. Actually, multiply both sides by a -4 to cancel out that negative there. And you're going to end up with a positive 280 degrees. That's our first angle now that we will use. Let's do that here. Next one. Multiply both sides by a -4. End up with 100. After that, we use our pattern. Now, this is an interesting pattern. We haven't seen this yet. We'll explain why it's happening in a minute, but for now, we're going from 280 to 100. We're actually going down 180 degrees. Kind of interesting, right? So we're going to repeat that here. If I go down 180 degrees from 100, then that's going to put me at -80. And if I go down another 180 degrees, that's going to put me at -260. And then finally, if I go down another 180 degrees, where's that going to be? 0, 4, carry the 1, negative 440. Those are my new weird angles that I'm going to be using to graph this tangent function. But notice they're backwards, right? The positive ones are over here and the negatives are over here. So when I actually put it on my graph, I'm going to start with this one on the left side, and I'm going to work my way up this way, going right. Let's do that really quick. So my lowest angle that I had was negative 440 degrees, and my highest angle was 280. I had two positive angles, 280 and 100. And then after that, I had the negative 440 on the other side. So let's just go down here a little bit. Negative 80, negative 260, negative 440. You got to get your angles in the correct order. Negatives on the left, positives on the right. Okay, that's a weird thing, number one. Now, why did it do that? Why did it get flipped? It's because my angle has a negative in front of it, which is a horizontal reflection. It flips everything backward. That's why that happened. Okay, but other than that, we don't really have a whole lot we need to worry about here. We're still going to have our vertical asymptotes at the beginning and end. And we're still going to plot the midpoint at 1 unit high. So from the middle angle, we're going to go up 1, and that's where the midpoint of my graph is going to be. At the middle angle, the height is 1. And then we're going to use the stretch factor. Now, this is where things get interesting. You guys know that usually tangent goes like this, but we talked last class about how whenever you have a negative on the inside, it flips your tangent the other way. So our tangent graph is actually going to look like this. It will not look like that. So using this stretch factor then, I'm going to go left 1 and up 4. Right 1 and down 4. And there it is. Okay, so got to pay attention to your signs here so you know which direction to go. Watch out for those negatives and those reflections. And if you forgot which way to go and stuff, then look at the notes from last class. That'll really help out. So here's one for you guys. I think I've already got the answer up. I don't want that there right now. Let's leave that off. I'm not sure if that was the answer or not. Why don't you guys go ahead and try to do this one really quick. Pause the video. And notice, by the way, that this one has a negative both inside and outside. Okay, what is that going to do? So go ahead and see if you guys can graph this one. So first of all, you guys should have found your angles. So setting the first two angles for sine, which are 0 and 90, equal to the horizontal transformation. We solve for theta and we end up with 0 and 180, which shows us that we're going, or sorry, negative 180, which shows us that we're going down by 180 degrees every time, which means that the angles I use will be what you see here. So I have I've got 4 negative angles and then 0. Okay. The next thing you would do is graph it. So I'll go ahead and bring up the graph now. Okay, so I put the angles on the graph. My midline is at positive 1. My amplitude is 2. Okay, but notice the direction. Now, you might be confused why the graph looks like this. Here's why. Remember how when there's a negative on the inside, that makes the graph go down? But so does a negative on the outside. So this is like a double negatives for sine. And when that happens, it just replaces it back to normal. So this one's still going to start at the midline and go up because there's a double negative. But remember, that would be different if it were cosine, which we talked about last time as well. But in this case, it really just makes these two negatives, in a sense, just kind of cancel each other out. But that does not apply to cosine, so be careful with that. All right. And so that being said, there's more. I think I'm going to wait on the rest of this for now till next class. Just kind of getting to be a little bit too much here. So we'll leave it at that, and you guys can go and do your homework at this time.